Okay, good evening, all of you. I want to thank all of you for this for this help to give me a presentation. So my talk is memory response in a two-dimensional plate with spatially varying heat sources and body forces. So outline of my talks are theoretical development of generalized thermoelasticity, different models of generalized thermoelasticity. So I will give a brief introduction and formulation of the problem, my problem, method of solution, numerical results and discussion, and finally conclusion. So let's start from classical thermoelasticity. It's a brief, the famous Duhamel-Newman relation, 1838. This is the stress-strain temperature relation, and this wave type equations of motion, lambda mu are Lami's constants, and tau ij stress tensor, eij strain tensor, and Fourier law of heat conduction. This is the classical Fourier law, energy equation and heat conduction. So this theory has two shortcomings. The first and obvious one is that the elastic deformation has no effect on the temperature field, and the other is that the theory predicts an infinite speed of propagation of heat waves, which is physically impossible. So after more than 100 years, Bayet, the classical coupled thermoelasticity, he actually introduced by correcting the first shortcoming. So he introduced a term gamma T naught delta dot. Actually, this represents a coupling between strain and temperature. So a direct consequence of the above temperature equation is that if the material is subjected to a thermal disturbance, the effect of the disturbances in both temperature and displacement fields will be felt simultaneously at distances infinitely far from the source, since two fields are coupled. So thermal signals propagate with infinite speed. But the second shortcoming was there, the heat propagate with infinite speed. So to take care of this paradox, several scientists actually have done. So one of them is Lord-SHULMAN, 1967. Actually, he modified the Fourier law by introducing a term known as thermal relaxation, tau naught. Actually, thermal relaxation, time lag needed to establish steady state heat flow in an element of volume when a temperature gradient is suddenly imposed on that element. Next, actually, modification has been done in the year 1972 Green-Lindsay model. So they have introduced two relaxation parameter, alpha star. So in both the cases, in these theories, the second error, that is the heat propagation, that is actually nullified. Most relevant, actually, the Green-Naghdi model 2. They have introduced three models, model 1, model 2, model 3, and K star is the additional material constant in this case. And this is known as thermoelasticity without energy dissipation because of the damping term T dot is not present in the equation. So it is a most important model. And model 3, that is in 1993, you see the heat equation contains the T dot, that is a damping term. So it admits the dissipation of energy because of the presence of the damping term. And very recently, not recently, it is in 2007, Professor Roychoudhury, they have introduced three-phase lag model. It's a very interesting and very famous model. And they have introduced three-phase lag parameter, tau T, tau Q, and tau nu. So tau T is the phase lag for the temperature gradient, and tau Q for the phase lag for the heat flux vector, and tau nu thermal displacement gradient. So they have introduced three lag parameters actually. And this is the heat equation. And next in 2011, Wang and Lee, they have introduced memory dependent derivative. So why people are using memory dependent derivative? That may be the question. The memory dependent derivative, that is the functional value in real time, depends on the past time also. That is why d tau, that is the memory dependent derivative, is called a non-local operator, whereas integer order derivative is a local operator. It does not depend on the past time. So this is the actually structure of our problem. So now let's come to the formulation of the problem. Let's come to the geometry first. Let me explain with the geometry. So we consider an infinite homogeneous transversely isotropic thermally conducting thick plate with spatially varying heat source at uniform reference temperature T naught in the undisturbed state. The upper surface of the medium, you can see that, is taken traction free. There is no stress and subjected to a known temperature distribution. The lower surface of the plate is laid down on a rigid foundation and is thermally insulated. Okay, so let the faces of the plates be x equal to plus minus h, plus h minus h, and so we are considering two-dimensional deformation of the plate. That is why the displacement vector u and t can be functions of x, y, t. So in this case, our constitutive relations can be taken as this equation 2, stress, strain, temperature relations, and the equations of motion, that is given by equation 3. And you see Fx is the body force that we are used to take. I will give you the form body force in later on. So next formulation is our Fourier law. This is our Fourier law, and we have taken three-phase lag model. Just already I described in the introduction that this is from Roychoudhury, Professor Roychoudhury model, three-phase lag model. They have introduced three, and also I am taking memory dependent derivative. So that is why it looks like the form 5. And heat equation, this is the form. And in my paper, I was using some dimensionless parameter to make our equation dimensionless, and those equations after dimensionless solved subject to the initial conditions and boundary condition. Look at the boundary condition. Theta equal to theta is a function of h, y, t, and theta naught and g are constant. H is a Heaviside step function. So let me go to the geometry once again. So the upper surface of the plate is actually heated on a band of width 2g around y-axis. Okay, so that is why the form is taken like that, and there is no stress. So these are the boundary conditions. And the kernel function you can choose freely as. So I have taken three types of kernel function, and they have a equal to b equal to 0. Kernel is 1 minus t minus zeta by tau, a equal to 0, b equal to half, and 1 minus t minus zeta by tau whole square if a equal to 1, b equal to 1. So there are three types of kernel functions I have chosen for my paper. And for and I have used for method of solution, I have used Laplace Fourier double transform, because you have two dimension in space and you have a time. So x, y, t. So I have chosen Laplace Fourier double transform. Also the equation 11 is the memory dependent derivative, Laplace transform of the memory dependent derivative. So after applying the transformation, the equation looks like 12, 13, 14, 15, 16. All the previous equations have been transformed, and after some manipulation, equation 17 is the Fourier law, and most complicated one is the heat equation. It looks more complicated one. 18. And elimination, and after some manipulation, calculation, we have arrived elimination of u bar cap theta and theta bar cap. We are arrived at equation 6-degree differential equation in v and theta, equation 19, 20, and these coefficients are functions of xi p, a, b, c, d, r, and r1. So these are most complicated form, and in our paper we take the spatially varying heat source in the form qxyt equal to ht cos bx by y square a square, and if you take the transformation, it will looks like this. This is the form of the function if you take the transformation. And body force in our problem, I have taken a body force along x direction. So fx is given by ht, Heaviside step function, e to the power minus bx by a square plus y square, and there is no body force along y direction. So after the transformation, they will look like this. So after solving and get a form of like 21, 22, that is the form of v theta, temperature and velocity, displacement along the direction, and also the coefficients are given by, and this is the equation where kj's and minus kj's are the roots of the 6-degree algebraic equation. So our differential equation can be converted after some manipulation, can be converted into algebraic equation so that we can solve numerically. So 25 is the algebraic equation. So roots of this equation can be complex, and substitution of v and theta that we are separated, it goes to 26. So there are a lot of calculations are there. So I'm skipping, I can't accommodate those calculation here. So 26, 27, you get a form of the u. So if you get u, you get everything: temperature, v direction, stress, normal stress, shearing stress, all. So let me go to the numerical results and discussion. So for my paper, material chosen for the plate is transversely isotopic magnesium, and the physical data have been taken from Dhaliwala and Singh. These are the elastic constants, beta was the stress temperature coefficient, thermal conductivity, specific at a constant volume, T naught, every. And for solving that polynomial equation 25, we are complex domain, we have used logarithm method programming. Okay. And also we have taken for numerical calculation K star equal to additional material constant for GN theory is 200, and tau q, tau nu, tau t, that is the three-phase lag parameter according to Roychoudhury, has been taken as this, and which agrees with the stability condition of Quintanilla and Rache, because we have to satisfy the stability condition, otherwise we can't use the model. And for numerical inversion of Laplace transform has been done using a method based on Fourier series expansion technique, that is by Honing and Hardy's in 1984. And so let's move to the diagram. You can see that we plot temperature distribution for different kernel functions. It is seen from the figure that the temperature distribution in the transversely isotopic body mostly decreases with the x direction. The maximum temperature attains near the lower surface of the thick plate, x equal to 0.5, and the temperature decreases to 1 at the upper surface of the plate, which satisfies the boundary condition. The variation of temperature is not linear but oscillatory. You can see that the oscillatory nature is there. Perhaps this is due to the fact that constant temperature load is given on the upper surface, and while the lower surface of the plate is laid down on a rigid foundation and is thermally insulated. Actually the lower surface is thermally insulated, so there must be some reflection. So it is expected that heat will penetrate from the upper surface to downward, and at the same time same amount of heat will reflect. And you can see the displacement also. So displacement u y equal to 0 for different kernel functions. It is clear from this figure that numerical results of the displacement components are found to satisfy the theoretical boundary conditions. That is, on the rigid base the displacements are 0, and on the upper surface the displacements are maximum, which is physically possible. And the last diagram, that is the stress, normal stress sigma xs kernel for different kernel functions. It is mentioned earlier that it is seen that sigma is vanishes at the upper surface because there is no stress on the upper surface, theoretical conditions, and oscillatory nature is also observed because of the reflection from the lower surface. So these are my conclusions, that according to this new theory, here we make a classification of the materials according to the time delay, where this parameter becomes a new indicator of the ability to conduct heat in a conducting medium. And these are the references. This is current references, and this is a paper from you, and thank you.